Wave motion. Before starting this video, please click the subscribe button. Please like, comment, and share. What is wave motion? It is a process by which a disturbance at one point in space is propagated to another point more remote from the source with no need transport of the material of the medium itself. An example of wave motion is to flick one end of a long string that is under tension and has its opposite end fixed. The pulse propagated along a stretched string. In this case, the individual points along the medium or the spring travel back and forth parallel to the motion of the pulse. And the easiest way to visualize what wave motion is water wave. When a pebble is dropped in a calm pool of water, ripples travel out from the point where the pebbles enters the water. The disturbance travel out from the center of the pattern, but the water does not travel with the wave. If I will put a crumpled piece of cellophane, then if you were to examine carefully the motion of a small object floating in the water, you would see that the objects move vertically and horizontally about its original position, but does not undergo any net displacement away from or toward the point at which the pebble hit the water. Wave motion has two types, mechanical waves and non-mechanical waves. So let us focus on mechanical waves. Mechanical wave is created when a source of energy causes a vibration to travel through a medium. So all mechanical wave requires first some source of disturbance. For example, in water wave, the source of disturbance is the energy of the pebbles, and next is a medium containing element that can be disturbed, which is the water, and three is some physical mechanism through which elements of the medium can influence each other. So mechanical wave is a wave which need materials for the propagation. An example of this is sound waves are mechanical waves since it needs a material medium for propagation like drums. Now, let us proceed to the types of mechanical waves. First is transverse wave. So, on the left side figure, a pulse travel on string is the pulse passes point P on the string. The point moves up and then back to the equilibrium position. Each segment of the rope moves only perpendicular to the motion of the wave. This type of traveling wave is called transverse wave. A traveling wave or pulse that causes the elements of the disturbed medium to move perpendicular to the direction of propagation is called a transverse wave. The ends of the slinky never leave the hands holding it. It's just the energy that moves along. In transverse waves, the disturbance that makes the wave is perpendicular to the direction which wave travel. For example, in the video on the left side, the disturbance that makes the wave is perpendicular to the direction which the wave travels. This figure is a transverse wave. The highest point above the rest position is the crest. The lowest point below the rest position is the trough. So the distance from one crest to the next is called wavelength or Greek letter lambda. So the next type of mechanical wave is longitudinal wave. So in this figure shows the pulse propagated along a stretched spring. In this case, the individual points along the medium or the spring travel back and forth parallel to the motion of the pulse. This type of traveling wave is called a longitudinal wave. A traveling wave or pulse that causes the elements of the medium to move parallel to the direction of propagation is called a longitudinal wave. An example of longitudinal wave is sound. When a drum is struck, the drum skin vibrates, which causes the air particles next to it to vibrate. This causes the next air particle to vibrate, then the next, and so on, until the vibration reaches the air, causing the air drum to vibrate. The vibrating air sprays away from the source, creating a sound wave. The figure on my right side is an example of longitudinal waves. As you can see, an area where the particles are spaced close together is called a compression. An area where the particles in a medium are spread out is called a refraction. The longitudinal waves are the faster of the two mechanical waves, traveling at speed in the range of 7 to 8 km per second near the surface. They are called P waves, with capital P standing for primary because they travel faster than the transverse wave and arrive first at the seismograph, a device used to detect waves due to earthquakes. The slower transverse waves, called S waves, with capital letter S standing for secondary, travel through the Earth at 4 to 5 km per second near the surface. Now, let us proceed to the wave properties. So first, we have here the wavelength. Wavelength is the length of the repeating wave shape, or the distance between one wave and the next. So wavelength is represented by the Greek word lambda. So as you can see in this picture, wavelength is the distance between one wave from the another wave. So now, let us proceed to the second properties of the wave. It is the amplitude. So amplitude is the maximum displacement of the particles of the medium, which is determined by the energy of the wave. It is the size of the wave's disturbance. The more energy a wave has, the greater its amplitude. So let us look at this picture. So it is shown that amplitude is the maximum position of an element of the medium relative to the equilibrium position. Next, let us proceed to the third property of wave. We have the period. The period is represented by the capital letter T. It is the time for one wave to pass a given point. The period is measured in seconds, the time it takes for a complete wave to pass one point in space. For an ocean wave, the period is the time between the two crests. So, the equation for the time is T is equals to 1 over F. So, if you count the number of seconds between the arrivals of two adjacent crests at a given point in space, you measure the period. So, next property of wave is the frequency. The frequency is represented by small letter f. It is the number of waves passing a given point in a unit of time. Frequency is measured in cycles per second, or the unit of hertz, with a dimension of seconds. For example, a wave generated at 60 cycles per second has a frequency of 60 hertz and can be expressed as 60 over 60 per second. So frequency is a reciprocal of the period. So it is expressed by F is equals to 1 over T. So the number of waves that passes through a given point in one unit of time is also called as frequency. So the higher the frequency, the shorter the wavelength. So as shown in this picture, as you can see, if the wavelength is shorter, then the frequency is higher. If the wavelength is higher, so the frequency is shorter. Now, let us recapitulate what we have discussed by the help of this figure. So, the highest point above the rest position is the crest. So, the lowest point below the rest position is the trough. So the distance between one wave and the next is the wavelength. And the maximum displacement of the particles of the medium is the amplitude. The time for one wave to pass a given point, and it is measured in seconds, is the period. The next is the number of waves passing a given point in a unit of time, and it measured in cycles per second, or hertz, is the frequency. From the definition of velocity as distance divided by the time, for all types of waves, the velocity is given by the following. velocity is equals to the wavelength divided by the period. This equation states that the wave will advance the distance of one wavelength in the time of one period of vibration. Because frequency is the reciprocal of period, velocity is also v is equals to lambda multiplied by the frequency. The velocity is dependent upon the characteristics of the medium carrying the wave. Now, let us answer some problems with regards to uh, wave motion. So, let's get a bond paper and marker. So, our first problem is that the distance between the two troughs of the water surface waves is 20 meters. An object floats on the surface of the water so that it experiences the vibration motion. If the time to travel one vibration is 4 seconds, then the velocity of wave is blank meter per second. A 20, B 15, C 10, D 5. So, our given in this problem is we have our wavelength of 20 meter our period, which is the 4 seconds, and what we want to get is the speed of the wave, or our velocity. So our solution would be like this. The equation for the velocity is lambda divided by the period. So let us substitute our given numbers. So our lambda is 20 meters, which is the wavelength, divided by our time period, which is 4 seconds. So 20 divided by 4 is equals to 5 meter per second. So the correct answer is letter D. Our second problem is, on a pond surface, there are two dry leaves 60 centimeters away from each other. Both move up and down like the surface of the water with a frequency of 2 Hz. When one leaf is at the crest and the other leaves are at the trough, and between them there is one crest and one trough. Determine the speed of the wave propagation of the wave. A. 20 centimeters per second. B. 30 centimeters per second. C. 80 centimeters per second. D. 120 centimeters per second. So, our given based on our problem is that the distance between two leaves, which is 60 centimeters, and our frequency is 2 Hz. So, we need to find out the velocity or the speed of the wave. So, the solution is this. So, this is the graph. We will draw a graph. So, this is the first leaf and this is the second leaf, which is their distance is 60 centimeters away from each other, and they have the same wavelength, which is 1.5. So what we're going to do is to get their wavelength, since they have the same wavelength. So we need to get their distance of wavelength. So 60 centimeter divided by 1.5 is equals to 40 centimeter. So now let us proceed to our solution. So speed of the wave. So speed of the wave, velocity is equals to frequency multiplied by the lambda, or the wavelength. So let us substitute. Our frequency is 2 Hz multiplied by our wavelength, which is 40 centimeters. So 2 times 40, 2 Hz times 40 centimeters is equals to 80 centimeters per second. So our answer is letter C. And I guess that's all for this vlog, and I hope you enjoy watching this video. Thank you for watching.